welcome to another video. This time I'm going to specify a new bytecode format so that the plum code is not just immediately run within the compiler, but that it can instead be compiled to a file, and you can then store that file, share that with someone, and they can run that file. The bytecode will be similar to like Java bytecode, but with our own instruction set that is built, that we already have. Alright, so let's look at the instructions first. The bytecode is somewhere in here. In the VM. I see. In here. Yeah, this is the bytecode that we already have. The bytecode is stack-based. We have a data stack and a call stack. And, well, there are instructions such as push padding, push a single byte, push 8 bytes at once, push 1 byte that is somewhere back on the stack, push 8 bytes that are somewhere on the stack, pop some bytes, but skip some bytes. There's jumping, there is returning, there is calling, there is arithmetic stuff, comparison stuff, and so on. Also malloc and free. Right, so what I'm trying to do here is this bytecode has been stable since, I don't even know, like a bunch of videos, because this is quite low level. Whatever changes I make in the language, whatever changes I make in the type system, in whatever, in the end they can all be lowered to this kind of bytecode, because this is quite universal. There are intentionally some restrictions in this bytecode. For example, you should not depend on the endiness. You should depend on in which order the bytes of an integer are stored. So this push 8 thing, for example, is supposed to push a 64-bit integer, and if you pushed something, then you shouldn't pop individual bytes from that and read individual bytes. That is not really enforced, I guess, but still, the bytecode is supposed to be portable and kind of leave that undefined. Also, jumps currently jump to an address. I think when I want to serialize this bytecode to a file, I actually want, I don't know, the offset in the file, maybe, something like that. And yeah, I think that's basically the main stuff. So I think what I want to do today is not actually do the encoding of that, but just write some sort of specification, maybe some sort of spec. Yeah. So this is gonna be ground.md, because I think the bytecode should be named ground. I have created a bytecode previously. It's called soil. It is quite cool. It is, most importantly, hang on, didn't even know. Oh yeah, in here. Yeah, that is a simple bytecode, register based, and yeah, there are a bunch of implementations for that. There's a compiler written in assembly. There's a C compiler, a Dart interpreter, one wrapper in Flutter that also debugs nice things. There's a JavaScript implementation, and there are tools for assembling a textual assembly to that. Yeah, but the main interpreter that is the most fleshed out is the soilzig interpreter, which, if you don't know, it is, let me show that maybe, oh no, repositories, I guess, and then soilzig, yeah. So this is an interpreter and a JIT compiler written in Zig. Depending on the platform, it either chooses the interpreter or the ZIG compiler. I think I've done like you can do like a comp time check. Yeah. So you just switch on the CPU architecture. I can zoom in. If we are on x86-64, then we compile that. That's because that's what my laptop has, and so that's what I supported. Right. However, this bytecode is quite not complicated, but I think it can be even simpler. The main part, my main gripe with this is that this is register based, but the code that I write, like the Martinez compiler, that compiles to Soil bytecode, but it doesn't really use the registers efficiently. Like all local variables within the function are just stored on the stack, and I think it is also like really easy to compile to stack-based bytecode. That is simpler conceptually to think about. That is simpler in the encoding usually, because the arguments are implicitly on the stack instead of having to specify registers explicitly. And I think writing a simple stack-based bytecode is maybe a better fit for Plum, especially because in Plum side effects are not handled via syscalls, via this kind of ambient just being able to execute a syscall and then somewhat magically happens. But instead, Plum is entirely stack-based. If the main function wants to print something, then it returns, like Haskell, some sort of monad that says please print this string and then continue executing this other code. So I think a bytecode that kind of reflects that by not having syscalls is maybe more fitting for Plum. So my previous bytecode was called Soil, and the new one I think is gonna be called Ground, which is somewhat related to soil, but it also means, but also it makes sense that plum, as a fruit, grows in soil and in ground. Like there's kind of a theme going on, and I think that's fine. Okay, so what I want to write down here is not really I guess a specification something of the bytecode. Is not really a huge, it's not really a real formal specification of something. It's more like some text that describes how the bytecode is supposed to look like. I think there's even, like soil. Yeah, here's soil. I think this has a specification actually. Yeah, spec dot something. Yeah, it kind of outlines like what registers exist, what's the instruction set, how's memory, how does that look like, and on all the different instructions that soil has. Yeah. That is fine, and there's a separate specification for the encoding of soil binaries, and you can see that there's kind of not verbose, but it is quite advanced. Like it has some magic bytes at the beginning, and it has these kind of sections which can contain bytecode or the initial memory or the name or labels or whatever. Because one additional gripe I have with soil is that it assumes that there's this ambient address space available that starts at 0 and goes onto something. And that means it's kind of difficult to integrate soil into existing code without like completely virtualizing the memory, without saying I have this, this array list of the memory or something. Just having soil run in the same address space as some other code is really difficult, and interoperating with other code is also difficult. I think that might be simpler if there's an explicit malloc and free, and if everything communicates with the outside world. Even like you can pass arbitrary things on the stack, even pointers and things like that. Yeah, anyways, I want to not have a complicated bytecode format in here for the ground bytecode. Instead, I want basically something that is only consisting of bytecode. There is no initial memory, there is no name or labels or description or other section. This is just bytecode, no magic bytes at the beginning, nothing. Yeah. Also, no registers, because we don't need registers. We don't have floating point instructions. Like, this is, the ground code is going to be even simpler than the soil bytecode. So let's maybe start by saying ground is a bytecode format for a stack-based. Well, I'm in the way. Whoops. That was the screen, not me. For a stack-based virtual machine. Okay. Yeah. Hang on, for soil, is there like some general disclaimer stuff in the spec? Yeah, you see, ground doesn't have registers. It doesn't have at least initial memory, and assuming that it owns memory. Instead, instead ground will only consist of bytecode. Yeah, this is still true. So I'm going to just copy that down here. So ground is a bytecode format for a stack-based virtual machine. Maybe there are separate parts of state. The bytecode that's maybe the bytecode itself consists of instructions. Yeah, the VM, that's the virtual machine, goes through these instructions sequentially unless it encounters a jump or jump table. Yeah. You can't reflect on the bytecode. Well, the bytecode can't reflect on itself. For example, to store pointers to instructions. This is ground implementations, the freedom to compile the bytecode to machine code and start it. The stack there are three separate parts of state. Bytecode. The bytecode consists of bytecode, bytecode consists of instructions, the VM, these instructions that are executed sequentially, unless there is a jump or jump table. The bytecode can't reflect on itself, for example, to store pointers to instructions. This gives ground implementations the freedom to compile the bytecode to machine code and startup. Next, stack. The bytecode operates on a stack. Most instructions, all instructions, implicitly, well, not implicitly, inspect the stack. Example by popping values and pushing values. The stack and like reflect is a somewhat weird overloaded term. Let's just write directly. The bytecode cannot store pointers to instructions. Gives ground implementations the freedom to compile the bytecode to machine code and startup. The bytecode cannot store pointers to the stack. Because something. This gives the VM more freedom on how to implement the stack. For example, whether it grows upwards or downwards. Yeah. That memory, some instructions, malloc, free, well, and then load store operate on memory, on heap memory. Yeah, this is especially useful for data structures with unknown size and communicating with the outside world. A ground program consists of instructions. That's it. You can run these instructions. You can initialize the stack. Yeah, depending on the program, you are expected to initialize the stack with some arguments. Yeah, the program, after running, the stack contains the result. Boom. These are the instructions. And then we have these instructions. think this is rather, like this should come in a separate locations section. Cannot store pointers to instructions or the stack. Nice. These are the instructions. I think it's just going to be a list. Push padding. Along with their encoding. And now I kind of have to think about how I want to encode instructions. Push 2 bytes of padding to the stack. Now an instruction count programs as while ground program executes. There are 3 separate parts of state. I want some section like communication with the outside. For example, a ground program, always uppercase, may expect a pointer to a string on the stack. Pointer to a string on the stack. And return the number of whatever words in that string. A ground program consists of instructions. Consist of instructions. A program is an encoding of such of the instructions one after another. The instructions are not aligned to a common size, but tightly packed together. These are the instructions along with the encoding in hexadecimal. This is like push pattern. I think this is the name for that. I'm gonna make that bold. Not entirely sure. Yeah, that is push. Next is a list of all instructions along with the encoding in hexadecimal. Two letters correspond to a single byte. Oh yeah, maybe that makes sense. Push 1. Push byte XX to the stack. Then there's 2. Yeah, that is interesting. That pushes 8 bytes. So this would be 1, 2, 3, 4, 5, 6, 7, 8. Quite big. Pushes the I think I don't want progress may not depend on the endianness of numbers. Or the direct. Yeah. Little Indian X. Using XX and YY to mark variables. The little engine pushes X. Little engine which is a little engine encoded. Little engine and the native encoding on the stack. Something like that. Must be aligned to 8. The stack must be aligned to 8 bytes. I think that is also a nice limitation. Yeah, next we have push 1 from stack. And then the offset, that is an int in here. You know what, I'm actually gonna yeah, 8-byte integers are always encoded using little endian. 8-byte integers are always encoded using little endian on the stack. VMs are free to choose any encoding, any 8-byte encoding on the stack. Amazing. Yeah, 03. Yeah, so much about you know, being space efficient. Well, pushes a byte from the offset X from the stack. 0 equals top, etc. Pushes 8 bytes from the offset X. I mean, come on, we can. Yeah, if there was more padding, then we can just say we have multiple padding instructions. For these, okay, maybe it makes sense. You know, if you want to reference something far away on the stack, that should be possible. But for pushing and popping stuff, you can just have multiple instructions next to each other. X bytes from the stack. Well, first the amount to skip. That may be big. Yeah, pops Y bytes below the top. Yeah. Okay, control flow stuff, and I think I'm just gonna have a different. You know, these all start with 0. Let's do some that start with 1. Yeah, so we have 1, 0, and which is a jump. 8 bytes, yeah. And jump to the instruction at offset X in the encoding. Amazing. Then we have. Oh, there's a slice. Well, that's not really supported, I guess. table. Yeah, the X byte encodes how many there are. Yeah. Now the X bytes encodes how many jump targets there are. After these first 2 bytes, there are 8 bytes per jump target. Each one encodes each one represents an offset in the encoding. The jump table instruction pops a single byte and jumps to the instruction at the index. Then we have the call, some address, calls the function at the given offset X in the encoding. The yum is supposed to maintain a call stack so that we return instruction returns to the instruction after this one. I'll maybe use oh no, this looks horrible. Wondering if that works. Well, okay. So we have calls indirect. Like call, but the target is not merely encoded in the instruction, but popped hang on though. This is the kind of stuff that why writing a specification makes sense. Like this, doesn't this imply that you do know the position of functions? Well, to do. See, this is messy, and it's nice that let's call this return. Yeah, this is returns from a function call. Yeah, then we have arithmetic, so that can be really simple. That's nice. So for example, we can do this. hang on, subtracts the first further up on this from the first further down on the stack and pushes the result as an integer. So then multiplying, nice. Divides the first further down on the stack by the second. Divide is, that's cute. Mods the first. This is true modulo, not the remainder. So the result is always positive. Yeah, 64-bit integers are always in the the encoding uses little endian encoding for 64-bit integers. And made by encoding on the stack. Okay, numbers are signed from, well, -2 to the power of something, 63, I guess, to 2 to the power of 63 on this one, inclusive, something like that. Okay. Let's make this even clearer. Not this true module, not the remainder. And let's see. put that on multiple lines. I like having each sentence on its own line in the Markdown source, because then I get kind of a feel for which sentences are really long. To be fair, I think in here it's also pretty readable. Nice. Yeah, I want a table here. Can I have a table inside a list? Hopefully. Pretty nice. Mm-hmm. I'm not going to say that memory has to be previously allocated with malloc, because it may also be that this kind of interacts with the host program in a way that the host program allocates memory, and then you can use that, and then or you return some memory, like stuff like that. That is, like this. Yeah, then we have a load one, which pops an address. Yeah, pops an address, 8 bytes, loads. A byte from that address and pushes that byte to the stack. I guess a length first. First pops a length, then an address, crushes the VM with the message that address with that length. After crashing, the state of the VM is corrupted. New instructions should be executed anymore. No instructions should be executed anymore, and allocated memory may not have been freed. Yeah. The address may be 0. Well, no, then the length. So if I'm just wondering, like, if memory allocation fails and your program can't handle that, you might want to crash without a message. But then you can just give 0 as an address. That's fine, as long as you use 0 as a length as well. Or you just give any address in there and length 0. Yeah, okay. Nice. Then, what do we do? Basically, well, this looks horrible. Is there? Oh yeah, there's a preview. Oh, look at that. That was clean. I like that. Oh, nice. And it's really nice that so many instructions just are a single byte in size. Yeah, there are ones that are bigger, sure, but yeah, those that manipulate the stack. Like or those that you push literals and stuff like that. Cool. Call indirect is kind of weird though. I think we need a separate instruction. And also, this up here is not quite correct. That I executed consists of instructions. Yeah. By default, they are executed sequentially. There are instructions for insertion and for instructions. Yeah. I like that, having a bit more space in between it. Yeah, the state of going through instructions requires an instruction pointer and a call stack. requires an instruction pointer and a call stack. But yeah, I don't know. The bytecode operates on a stack. All instructions inspect the stack. For example, by popping values and pushing. For example, by popping and pushing values. Programs. Yeah. On programs cannot behavior. They can't directly trigger behavior in the host. Well, now the question was, what's a host? You know. Yeah, gets difficult. Nice. Cool. Okay. Yeah. I think that's basically it. Yeah, next let's... Oh yeah, there was one to do. Yeah, indirect calls. We use these for lambdas. And I mean, for lambdas, we kind of need to have some data that represents which function should be called. So I think we do need something like function pointers. But I think I'll have a separate instruction for that actually. So yeah, this will be instruction 14, this will be 15, and this will be I mean, yeah, we can just, yeah, I think that is fine. Yeah, okay, actually I think this is fine. Call indirect can just pop 8 bytes, interpret those as an offset into the encoding, and then jump there. Yeah, that makes sense. Okay, that does mean that at some point we need some sort of mapping between the, for an indirect call we would need to have a map. Like if we did compile the bytecode to machine code and we encounter a call indirect instruction, then we would have to basically look up in a map, hey, where is that actual instruction where we want to jump to? Do we want that? I don't know. I don't know. I mean, what's the alternative? The alternative would be having some sort of, you know, push indirect instruction. I think that's actually fair, yeah. Pushes an 8-byte token that represents the offset X in the encoding. Yeah, has to be indirect call token previously created using push indirect. Yeah, I think that makes sense. That makes sense. That kind of allows us to have a really, really efficient, well, why is that not updated? Oh, I don't know. Okay, yeah, that is nice. So now let's compile the, I don't even know, like, should I first compile Plum to that bytecode? Or should I first create a VM for that bytecode? I think I should first create a VM. Yeah. However, I think that should not be part of Plum. I think that should be, because the VM, like in the long term, I expect, I want to basically want to say, hey, Plum runs on the ground VM. This is the spec. You can implement that, and then you can run Plum programs. And also say, like a default implementation, if you don't want to write one, is this one. But basically, I don't want to tie Plum to that one implementation. I don't want to have one blessed implementation. Yeah. Because that's the idea behind having this kind of portable, layer in between. All right, so I think I'm actually going to create a new project, I guess. Ground Zig, a Zig implementation. Yeah. I think there was like a Zig in it. Something like that. Like that. Yeah. Okay, that is pretty cool. Yeah, let's open that folder. Okay, I wouldn't have thought that I'm gonna do Zig programming today, but that is fine. Okay, I won't go into too much detail about Zig. It's a language similar to C in the abstraction level, but kind of cleaned up and a bit easier to use and better tooling. Like you can see that we have type hints in here, that we have nice jump to definition, that things generally, like C, but things generally work, you know. Yeah, and it also has a bit like a better tooling regarding memory allocations and stuff like that. Okay, so the first thing I'm gonna do is just print stuff. Debug print. Welcome to round. Well, no, not really. Let's not do that. Yeah, this is I'm not gonna do that right now. Nope. Nope. Okay. What we want to do is we want to write some sort of zig program that I think we can like do zig build run or something like that. Yeah. Okay. I'm gonna should I put myself on the top right? Or is that fine? I think that's fine. You see, we have nice autocompletion and stuff like that. Hello, hello ground. Yeah, the arguments have to be like a struct. That's zig being weird. Yeah, hello ground. That gets printed. That is pretty nice. Yeah, I think I'm gonna put myself over there so that I don't hide the output in the console. Okay. I think first let's write some sort of VM thingy. And I think actually this should just have a run function, you know, that takes a program which will be some slice of bytes, and it returns something. Yeah. Also an input which will be a slice of bytes. The initial stack. Yeah. And then what we'll have is some sort of instruction pointer. Starts at the beginning. We'll have a call stack, which will be an array list, I guess. And then we put the standard lib, which is just defining a variable called standard. Okay, so we have an array list of bytes, and oh yeah, we need allocations. So let me take an allocator. I think LE is the thing you usually use for that. That's going to be a standard and that's pretty wide. Yeah, and in Zig you have to handle allocation failures, so see. Maybe put me down there first. Yeah, so because well, okay, this can't actually fail, I think. Yeah, when we have a call stack, we have a data stack, and initialize the data stack. That's what we're going to do first. We're going to do that by creating, well, by copying the input into the data stack, actually. So for input, I think you do like that. It's been some time since I've written Zig code. I think you do datastack.append or push.append of that byte. And you try that because that can fail. Boom. then run the code. And that's just going to be a loop which doesn't exist. We have while though. Yeah, while true, we do the following. We do it would be nice to have some sort of, you know, program read byte thingy. Basically bundle up the program and the instruction pointer, and by reading things from the program you automatically advance the instruction pointer by the correct amount. That would be pretty amazing. Yeah, so let's maybe create some struct bytecode. So bytecode is a constant that happens to be a type, which is a struct with instruction pointer, and the program, which is going to be a constant size thing. And this is kind of obvious, so I don't like. We don't need that. The bytecode is the bytecode. I think we can just do that actually, like that. Yeah. Now where the instruction pointer is 0, and is that a colon like that? Oh, like that. Oh, weird. And the program, well, that's just our program. We don't use this. We don't use these directly. Instead, we have these two stacks. Okay. Yeah, and then here we run the code by just saying program.read byte, and this is going to be a function down here. Read byte is going to return as a U8. It's going to accept a self, which is this type, and we'll do self.program of self.ip, it's the byte. Then we say self.ip plus equals 1, I hope that works. And then we'll do, we'll return the byte. Yeah. And similarly, we'll have some like read int. Oh yeah, we'll actually have the bytes from instruction pointer, well, to self ip plus 8, something like that. Or we just do it like that. Yeah, that's an 8-byte slice. Then the int is, I think there's like a standard int, read int, standard mem read int. Look at that. Huh. I think it wants the type that it returns. Okay, that's going to be an I64. The buffer is going to be our bytes, which has to be the size of the T, the I64, in bits, aka 64, divided by 8, which is 8. So this has to be a buffer of exactly 8 bytes. And the endianness is going to be little, like that. Yeah, and then we advance the instruction pointer by 8. Okay, yeah, that seems about right. So now we can do this. We can say opcode is program.read. Then we switch on the opcode, and well, if the opcode, oh, hang on, now we just look through, Oh, hang on, no, this is bytecode.byte. This, yeah, let's not use that right now, maybe, or like do this, I guess. Yeah, local variables are never mutated. Consider using const. Yeah, sure. I'm wondering why we don't get errors. Oh yeah, this is similar to Martinez, by the way. You know, if you don't use code, you don't really get errors for that. It's kind of cursed. Yeah, so the run function is public, which means we can do, we can just import that. We can do import the vm.zip run function. Boom, then we have this function. And then we can say, please run the program consisting of, well, and then we can think of something. Let's maybe write a really simple program by hand. Oh yeah, that would be plum ground.markdown. Yeah, let's push this, push an 8-byte integer, which would be this 2, and then, oh, you know what? We can even do something a bit more clever. We can say we want to have, I think this is an array. I'm not entirely sure. Yeah, 2, and then just what would, I think we want to calculate 2 plus 3 or something like that. 1, 2, 3, 4, 5, 6, 7, 8. That would be the first instruction, like push 8, 2. We'll do the same to push a 3, and then we'll add them using the add 8 instruction, which is 2, 0, coincidentally. And without any arguments behind that. So this is add 8. Okay. Ooh, I mean, we can even, yeah, let's not do that. Let's do this. Let's take that and pass that in as the initial input. So this is the program that adds 2 to the input. And it, well, we call that with a 3. And that is supposed to run something in here. Okay, so the tooling is not working exactly as it should. Expected 3 arguments from 2. Oh, an allocator. Okay, luckily there is something called a general purpose allocator. No, standard GPU. Standard mem, maybe? General or default allocator. I'm actually not sure. Let's look. The Ziglang stuff. Yeah, we have a testing allocator in here. Okay. More code examples. Standard out writer. Standard heap general purpose allocator. I see. Yeah, there's also cert that we. I'm just copying that code. Okay, so we print hello ground. Perfect. Then we created general purpose allocator, which we'll just call GPA because we don't have many variables. Oh, that is already that. And that is L. That is the formatted version. That is certainly interesting. Okay. yeah, this does not support invert array link. Oh, I see. So what we want is really this. That requires an ampersand to a slice like this. Yeah, okay. Okay, now we're getting somewhere. Now we get errors in here. Oh, but not in the IDE. That sucks. Okay. Anyways, we have this nice specification. So we can just copy that, paste that in here, and be like, oh, there's 0, 0. Actually, hex 0, 0. That is push pop. So push X bytes of padding to the stack. Or just be consuming another byte. Padding is bytecode read byte. And then for that many times, we basically just do data stack.append padding zeros AA something. Oh no, this is gonna take a while. Next we have push 1 that pushes a byte. Then we do push 8. Well, and now comes the interesting part. Yeah, I think that is that's gonna be a common thing, pushing and popping integers. So I think I'll actually have some sort of data stack. Which contains the bytes, which will be an array list of 28 standard array list. Data stack dot, there will be an init function that's going to return a data stack, and what it does is without this, it's just going to create a thingy like this with bytes being standard array list with init with an allocator. Something like that. Yeah, and then in here we can do data stack is not really just an array list, but really it's a data stack. Well, dot init. Amazing. And then we have functions for pushing and popping byte. Pushing a byte is just, well, self.bytes.append the byte, getting byte at an offset. I don't know. That just gets the byte, so this does self.bytes dot self.bytes.len minus offset minus 1, something like that, and then there is pop byte, which does just that. This can fail. I feel like this part right here kind of makes it so that tuning is even worse than it already is. Yeah. Yeah, exactly. Yeah, data stack dot push byte. And we do data stack dot push int of that value. Amazing. Yeah, pop byte doesn't really do that. Okay. Yeah, this should return a U8, just like this, by the way. And then we need the same for ints. It's going to be a bit more complicated. Yeah. Yeah, selecting that is kind of weird. Okay. So push int. Self.bytes append int. Well, not really. We'll get to that. And then we do standard dot mem dot read int. Yeah, there's just called get int. Let's maybe do that first. Okay. Nice. This does, well, int is self dot get int at offset 0. Then we do self.bytes.length items.length minus equals 8, please. Oh, I hope that works. Seems cursed. Modifying the internal stuff from that thingy. But I guess. Yeah. Oh yeah, and this is supposed to add that by getting, well, standard mem.write int is something like that. Hello. Maybe not. Yeah, append is not a thing. Oh, no. Instead we do data stack.push byte. That is nice. Yeah, that is, oh yeah, we try that. That's nice. Error union is ignored. Instead of using try, catch, or something. Yeah, true. Let's use try. Alright. Alright, this looks fine. Self.bytes.append. Why is that? Oh, I think because we need to accept mutable versions here for the pushing and popping. Switch must handle all possibilities. Oh, same here. These are mutable versions. Yeah, okay. That's pretty nice. Let's maybe add an, it's called else, hopefully. Yeah, return error invalid. Good. Something. No field named mem in VM data stack. Oh, self.mem. No, standard.mem. It does accept a buffer. Strange. So we can just say buffer is that. Does that work? And then we say, well, let's please store an i64 in that buffer using little endianness. Nope, it has the buffer, then the value, which is the int. Strange. Okay. What, isn't it like passed in down here? Or do we have to do that? Probably. Makes sense. And then for every byte in the buffer, we basically do self.bytes.append that byte. Something like that. Okay, yeah, can we fill that somehow? I mean, if not, that's also fine. Yeah, no, you know what, I'm just gonna do that. 1, 2, 3, 4. 1, 2, 3, 4, like that. Otherwise, it's gonna give us an error. So, okay, expected 4 arguments, found 3. Hang on. Oh, the T. It does accept a T. Okay. Value of type something is ignored. That is indeed true. Yeah, that returns the output. I mean, it doesn't really, because it loops forever. Unless it returns an error, but that is nice. I think you can do, no, that was Rust, like that. I think you can do hashtag, not entirely sure. Nope. I don't know. Something like question mark. Just question mark. Any seems perfectly fine. Yeah, that's nice. Okay, so in 132 we read an integer, and that is supposed to return i64. Okay, there is stuff going on. Memory address leaked. Okay, that is actually not fine, you know, but I think it is okay for now. Now let's not do that maybe. Ground error invalid opcode. That is perfectly fine. Oh, I see. That is leaked because what we want to happen is I And we have the bytecode of the program. We have the call stack. Here we also want to defer cleaning it up. So call stack dot init. Isn't there something like that? Free. So look at those examples again. Maybe array this, but it's not .d. Yeah. And we'll probably have to add a dinit function for that. Okay. Yeah. De-init that. Beautiful. Okay. Very good. Now let's re-enable that debug cert and still that. Okay, so we're freeing all memory, even if errors occur. That is nice. So then, invalid opcode. True. Let's maybe print the opcode. Would be useful, right? Debug print opcode. Let's maybe do that in hexadecimal. I think that is with X. Not entirely sure. Yeah, opcode is 20. Oh yes, that's the add. Beautiful. Okay, so we have this, we have this. I think it would be really cool to have some, some sort of thing with harsh assertions for all these invariants in there. That would be super nice. Yeah. The else thing, I'm just going to put that down here. And then over time I can just add more of these instructions. So the add, for example, it's going to pop two integers. Oh, no, but not from the bytecode, but from the data stack. Dot pop int A and B. And then it pushes A plus B. Nice. And yeah, let's do the same with subtraction. I think that's actually the correct behavior. Like if we have 3, 2 on the stack and we do sub, then we want to put 1 on the stack. Yeah, so the topmost thing further up on the stack is subtracted from the first one. Then multiplying things. And dividing. Hang on, we should also do that. Actually do that. Oh, dividing. Oh, that's gonna be interesting. Oh, mod should not be 23, that should be 24. and then 25, compare 0. Yeah, where we only put one integer, and yeah, if that value equals 0, then without then data stack result less and greater, greater less, sure, and then we do data set push byte of the result. So that's a byte. Let's double check that that's correct. Okay, greater than 0 means 1, less than means 2. That also makes sense because E is the first, then equals, then G greater, then L less, alphabetically sorted. Okay, nice. Next, ending to integers bitwise, and that's this in Zig. There's OR, which I think is that. There is XOR. And we have AND, we have OR, we have XOR, that is probably this rooftop thingy. Alright. Cool. It seems doable. Now it seems doable. Oh yeah. Hell yeah. Div trunk is probably the one I want. Like, I know they are different. Div trunk, I think, just truncates number, aka it rounds it towards 0. Div floor takes the lower one, like actually lower, and div exact they have to match. Like div exact is definitely not what we want. I think div trunk is what we want, but that should be specified in the documentation. You see, this is the kind of stuff that makes sense. Division always rounds towards 0. Div trunk in Zig. Okay. And it makes sense thinking about that. Like, this is why I like Zig for these kind of things, you know. It forces you to think about edge cases. Yeah, same here. RAM versus mod. But I think I've made the thing there pretty clear that I want mod, not RAM. Amazing. There no field named len in this struct. That may actually be, yeah. The M183. 183 is down here. Yeah, self.bytes doesn't really have a length, but the items in there do have a length. And that is super weird. Yeah, the offset has to be positive. I think we can do like an as. That kind of thing. Int cost. so as then using the type inference to make the int cast correct. That's horrible. Yeah, that is not really an array type, but it does have items which are slice. Okay, out of bounds. Oh, yeah, we've run to the end of the program. Actually makes sense. That is pretty cool. So, return. Where's return? And in here, yeah, 15, let's implement that. Return. For now, we'll just check if the full stack dot items then 0. Then it's gonna return the output, the data stack dot dot bytes dot items. But I think then that is not freed. I'm not entirely sure. Else, you know, for now to do. That is not relevant. What's a to do? To do in Zig? I don't know. Output segmentation folder, that was something. Okay. So we have output any being given output. Oh, I see. And that returns, makes sense. So the data is not really yeah, so this before this returns, this defer runs and the data stack is freed, and then there's just accesses invalid memory. So I think what we want to do here is actually, I guess, copy that to another buffer. Yeah, output is a buffer. Ali dot alloc bytes, please. How many bytes? Well, data stack dot bytes dot items dot len bytes, please. Yeah, that can fail, so this is in a try. And then we do a memcopy with a destination, which will be output. And the source will be data stack dot bytes dot items. Yeah, and then we just return the output. It's never one, but okay, sure. Well now, oh, this is interesting. This is really interesting. To 5. That is kind of weird. And 1, 2, 3, 4. 1, 2, 3, 4. Hang on. Oh, this is one too many, right? Oh, yeah, this was the instruction in front. We don't have that yet. We'll just do that. Okay, yeah. Now we have the 3. Okay, hang on. We have a program that pushes a 2 to the stack. Then it adds 2 8-byte numbers that are on the stack and then returns. And initially there's a 3 on the stack. So the program pushes a 2, adds that, so we have 5, and it returns. And that's exactly what we see here. That's pretty cool. Sadly, memory leaked. Let's see where that happens though. Oh, okay, it's pretty cool that this is what? That you get a stack trace to where the memory was allocated. That is nice. That is really nice. Yeah, because we need to free the output down here. So le dot free the output in the end. Before, after printing that. Yeah. Oh, look at that. And no memory leaks. Everything running smoothly. I mean, that's just cool. All right, yeah. I think now let's implement the other instructions, I guess. Yeah, so we have some call instructions and so on. We have malloc, and oh, this is interesting. What do I want to do? Yeah, I think I'm gonna do this first, and then only then do allocations. Maybe I can even do like a simple Fibonacci. I think that would be pretty cool. We'll see. So push 1 from stack. That would be 3. And what we do is we get the offset. That is bytecode dot read int, and then we do data stack dot push dot get int. Oh, hang on, get byte. Yeah. Add the offset exactly. And we push that. So we do data stack dot push byte. That byte. This can't actually fail, so it's more like that. Yeah, then instruction number 4 is push 8 from stack. Very similar, except that's an int, and here we do push int and call that int. Yeah, then we have pop. Where we just pop that many bytes, I guess. So that would be 4. Yeah, something like that. Okay, now this is interesting. Oh, hang on. Maybe first we have the amount. No, not the other way around. First we have the amount that we want to skip. Then we have the amount. And I think what we want to do, this is interesting. This is interesting. Is, well, I guess data stack. Top and below top. Yeah, I think for these stack instructions we should just add functions. Yeah. So pop below top. Pop n is pretty cool. That just does for n. It does self, which is a pointer to this. Yeah, we do self dot. I mean, self dot pop byte would also work. Yeah, and then we have the pop below top with self being this thingy, and then we have some amount of bytes to skip, and we have the amount. Yeah, let's call this amount as well. Yeah, and what we're doing here is we want some sort of mem copy. But that no alias is kind of that is what if they can overlap? Yeah, because the two memory regions must not overlap. I mean, yeah, let's just do a for loop, I guess. Why not? So for skip. Yeah. Basically, I want to say self dot bytes dot items at self dot bytes dot items dot len minus skip. Does that make sense? If skip is let's say the amount is 0. Well, okay, that doesn't make any sense. Okay, but then these should be the same, and these are the same. But these two, if amount is 0, they are the same. That is already promising. If the skip is, if we want to skip 1 byte, then we will read the byte at, length minus 1. Yeah, that is the last byte. And remove that from that last position to self minus 1 minus amount. Yeah, amount to the front. That seems correct. And then we'll do self items.len minus equals the amount. I think that is actually perhaps more efficient way to do that. Although I think most compilers will actually optimize that. This for loop of popping stuff. Yeah. And this would just be data stack dot pop amount. pretty cool. Pretty cool. Popular top, done that. Then jumping. Oh, that is interesting, because that adjusts the instruction pointer. The target is what comes next, so that code will read int. Nice. Then we do instruction pointer equals target, well, okay, as, oh man, as a usize, I guess, please, using an int cost of the target, something like that. And IP doesn't exist because that is bytecode dot. Nice. Then here we have a jump table. That's really interesting. So first we have the num, which is bytecode.read byte. And then, oh, we can allocate targets. Do we want to allocate memory for that? I mean, I guess we have to. Yeah. Because stack allocation is kind of weird. Yeah, the targets are going to be usizes. And please n, we want to have n targets. That can fail, sure. And then for num, we just say targets I equals, well, bytecode.read int. Oh. Yeah, why extract them and then later on, like, no, we don't need that. We can just do byte is datastack.pop byte, and then extract the target as bytecode dot. Well, you know, jump table stuff. Yeah, we have read int. We also have get int that takes an offset. And it doesn't use the IP, the offset, doesn't adjust the offset. Yeah, and then this can also just be, you know, self dot get int at the self IP offset. Then return that. Yeah, and this, hang on, this, no, hang on, this. Yeah, I can then just say get int. At, well, bytecode dot instruction pointer is 8 times the byte. That is pretty cool. That is so cool. Oh, that is nice. We don't even need to advance the instruction pointer for all of these, because, well, we changed the instruction pointer anyways, so I removed the byte. We don't even use that. Okay, let's assert that the byte is within bounds. Okay. If byte is less than num, if byte is less than, no, if byte is greater or equal to num, then that's an error. Out of jump table bounds, I don't know. Expected type I64 from use size. That is true. Now this is an I64, I guess. That is the use size. This is, I think we can just do as use size. Oh, I see. The get int. Yeah, I expect that except a use size. Sure. No field named len. Hmm. 204. Expected type use size, found I64. We're slowly getting there. We have a range maybe from 0 to that. Yeah. That works. Nice. Pretty cool. Pretty cool. Okay, so we have a jump table. I mean, we should test that, you know, but, well. Okay, then there's target, which is bytecode read int, and then we say bytecode dot, hang on, say call stack dot append the current instruction title, and bytecode IP equals target. Yeah. Okay. Yeah. Push indirect. I mean, target is just an int. And then we'll just do data stack. Push in of that. Simple. In other implementations though, when JIT compiling or mapping instructions to something else, that might be something different. So push indirect, then we have call direct. And that is bytecode read int. And then similar to the call up there. So it's just call stack append bytecode IP, and bytecode IP is the target. Nice. Okay, that is pretty cool. That is super cool. Yeah, the call stack should not be const. No, the call stack should be a variable. Oh yeah. Oh, hang on. No, the call stack actually should be use sizes, because the IPs are use sizes. Yeah, that's very true. Where's that? 72 in here. So like that. And basically the same down here. And here, when we are returning, and actually we'll just do call stack dot pop. Yeah, and we'll just do byte code.ip equals that. Pretty cool. Pretty cool. Yeah, that is nice. And the third part would be the heap. Oh, it's nice that you can really see the three pieces of the code. Like the bytecode, boom, the data stack, boom, and then the heap. In our case though, like I want to have multiple implementations of the heap, basically. One that just uses the allocator, the simplest version, but one that also checks more stuff. By, I guess, having a list of, having kind of a virtual address space, just having a list of bytes and giving out addresses and tracking which ones are freed and stuff like that. Yeah, but this one is just gonna have the allocator. And it's going to have something Yeah, we need to malloc stuff. We need to free stuff. Okay. That's fair. Alloc, I guess. Yeah, that is kind of overcomplicated. Let's just do that directly in here, and we can always factor that out later. So first pops an alignment. That is going to be 1 byte. Then size, that's going to be allocates memory. It will be le dot alloc hang on. Yeah, that seems fine. Alignment is U29. Okay, sure. And we have a size. Cool. And I can fail. Oh, I see. Pointer is buffer dot pointer. Can I int from pointer look at that to get an int? That's pretty cool. That's actually pretty cool. And then I'm gonna do data stack dot push int pointer. Let's see if that works. No, it does not. Oh, the alignment has to be. Come on. Why does it has to be compile time known? Oh, I see that. Still compile time known. Comp time alignment. Why is it raw alloc? Okay, raw alloc seems fine. Okay, with a runtime known alignment, that is fine. So we have a length I don't like that. What is the return address, by the way? Weird. Okay. Yeah, I guess that doesn't work. I guess we'll have to do something hacky. A comp time switch over the alignment. No, not really comp time, but if the alignment is 0, yeah, something like this, it can't be 0. If the alignment is 1, then we'll just pass 1 as the alignment. If the alignment is 2, then we will pass 2 as the alignment. If the alignment is 4, then we'll pass 4. If it is 8, then we'll pass 8. Otherwise, we'll just return an error. Okay. Man. That is, wow. Expected type U size found I64. Yeah, size. Let's cast that to a U size, I guess. And also let me take a break after that. Push int of some pointer. Expected type I64 found U size. True. Okay, that works, at least. Yeah. Okay, so I'm gonna take a break and then do some stuff. Okay, next, freeing numbers, freeing addresses. That just does free of that memory. And we can do like an int, like a pointer from int. And I think they can't fail. Not entirely sure, nope, it can't. Okay. Nice. Yeah, freeze the memory of that address. Cool. Then store 1. First, pumps a value, which is a byte, then an address, 8 bytes. Then we do pointer from int of that thing. Oh yeah, and that should be a pointer to let's call this address maybe, and make this a pointer to a U8. Then we can just assign that like that, storing a byte in that pointer. That seems correct. Then the same thing for storing 8 values. That would do something. I don't know, value is datastack.pop byte. Store 8. Yeah, the value now is an int. And the pointer kind of points to an I64. So we can assign that. Beautiful. Then we have loading. Loading single byte does not do this. It just pops an address. Then that is the vector, and then pushes that. So data stack dot push byte. Let's do that in line here. And then load 8. 45. Hang on, pops an address 8 bytes, loads 8 bytes from that address, and pushes them to the stack. Perfect. Okay, then we have crash. That is the final instruction. First pops a length. Which we're gonna cast to a usize. Then an address. That is datastack.pop int. Then we create a pointer. Is there like a pointer from int? From that address, please? Yeah, that must have a known result type. And that is a pointer to U8s. So creating a slice. How does that work? Now, here we have these array lists. The array list turns array list aligned. Okay, sure. That is that. That is just a slice. Slice is defined down here. As that slice of t. What I'm wondering is how does the allocated slice new memory as a slice aligned alloc. Oh yeah, I see. Yeah, that returns a slice. Okay, I see that. Hang on that are those items? Yeah, I can do array list.items dot len and dot pointer. Yeah. So I think I can just do that. So I can kind of do a slice is undefined, and then the slice dot pointer equals pointer from end slice dot one equals len, something like that. I don't know if there's a syntax to do that directly. Can I do something like this maybe? Is slice just a struct? I have no idea how that looks. Yeah, let's do like a debug print of that as a string. Pointer from int must have a known result type. M155. free some address. Okay, so this is just a pointer to U8. Yeah, okay, so this is an I something. So this is actually, I need to cast that. Okay, 173, very true, this can fail. U8, okay, so that doesn't work. But I can do this. That is cursed. That is really cursed. Yeah, let's see. So we have this allocator stuff, meta expected pointer, slice, array or vector type found, pointer to U8. That is a pointer as far as I know. That is weird. Is it this one, maybe? Oh, where's the other? Oh, come on. Just want to see where the error comes from. No, not there. Okay. So somewhere here, probably the free part. Emitter. Allocator 308. Yeah, this. Mem.slice as bytes. What is that even, like? Bad. Int please. That is a interesting, sure. Crazy. Nice error messages. Int please. Cool. Yeah, I wanted to look at the basically creating a new slice from a pointer. No, hang on, I want to free a pointer. Yeah. There's any type, but I don't know what, like, this is a pointer though. What? here we do given a slice, return the slice of the underlying bytes. Okay, no, we don't have that. We don't have a slice. We don't know how many pointers, how big that is. Well, what do we do? What to do? Could not, like, I could say that free also, the free instruction also accepts the size of the memory that is to be freed. That actually, I don't know, at some point I saw some talk where they said that this is basically, this probably makes more sense anyways, because at the point in the code where you want a free memory, you also have the information of how much memory there is. So that's not really an extra thing that you need to think about. Free memory is easy. But as the implementer for an allocator, maybe you don't have that information, just the receiving pointer versus a pointer and a size. The size might tell you more information about where that was allocated or something. Like, not where that was allocated, but, you know, I don't know, maybe free should also accept a length. I don't know. I mean, this is how it is here, basically. Yeah, they have the bytes. Which is the bytes.len. Yeah. Oh, that's a common theme. Okay, interesting. Returns the slice as bytes return type. Interesting. Yeah, okay. Let's do that. Let's say that pops an address, 8 bytes. Well, you know, first pops an address, then a size, and frees the memory, which has to have the size. Yep. Nice. So we have that. Then free should take the address, then the size, and the memory is basically a wait, slice. Hang on, I saw some, what was it? Yeah, slices bytes. Oh, no, not really. Well, okay, never mind. Yeah, memory.pointer equals pointer. Memory.len equals size. And then free the memory, please. I mean, sure. That is nice. That is really nice. Okay, that compiles. Now let's. I'm actually not sure what to do. Yeah, let's use that. Let's try that out. Let's. We do already do this. So this is. That. Yeah. In the Plum VM we had this kind of nice debug printing for objects. I'm not sure where that was though. Yeah, this right here. I'm not sure how to print hexadecimals with padded stuff. The call state, I don't care about that right now. Ooh, That's pretty cool. Oh, that is nice. Initially the data stack just contains a 3. Then it also contains a 2, then those get added to a 5. Amazing. Yeah, apparently this is not like this, maybe? Nope. Oh, I could just go into the... Yeah, let's do that. Let's go into the formatting code and see what happens here. So we are formatting something. We are formatting some placeholder, yeah, with a number. Placeholder.parse, interesting. Parse until colon. And then we do this. Oh, I see, left aligned, or this, or this. I see, so this should be right 0. Then the width, position, okay. So I think that should just be like that. No. Okay, let's Google. Well, let's zig format numbers. Okay, so you're going to do D for decimal, I guess. Well, that doesn't tell me anything. Okay, hang on. Do they have maybe docs? That would also be nice. Well. Oh yeah, there is documentation. That makes sense. Hey, format stuff. Yeah, we don't have that, no. Yeah, hexadecimal please, lowercase. That's the specifier. Okay, we don't have that. Then we have X. Then we have a 0. Then the alignment, then the width. Something like that. So like that. Indeed. Seems to work. That's pretty cool. Yeah. Nice. Cool. Very cool, actually. So let's build something. Let's say we want to create a Fibonacci program. Even better, let's say we have some sort of let's write some tests maybe. that tests simple instructions. Yeah, so we want to say push padding. And pop. And what we'll do is something like this. Testing locator. So I think we want to push 2 bytes of padding. And then we want to pop 2 bytes, I guess. Yeah, we want to return. How do tests look in Zig? Expect equal. Okay, so we expect to get this kind of thing. Okay. Oh, hang on, that is not working. Well. Hang on. We push 2 bytes of padding, then we pop 2, then we return. That is supposed to be empty. What is going on there? Like what? Data stack is nothing, then it's AA, makes sense. Then it is nothing again. Oh, hang on, this doesn't compare slices, it actually checks that they... Oh yeah, oh I see, this works for the... I need to check the individual bytes. Oh man. Okay. Let's have a function, expect output. Oh, functions use camel case by default. I haven't done that consistently, I'm afraid. Yeah, so what this does is it takes a program, which will be a U8 constraint thingy. It will take an input. Which will be a U8 times 2 8 even, and an expected output. And then we do this. And then we can just do try expect result. We have a program. We have an input. And we have an expected output. Okay. Ooh, that is nice. That is super nice. So we test push padding and pop. What else? Let's try push one from the stack. Push one from stack and hop below top. So we have push one and one. Same with the two, push one, two, boom. And then we do push from stack, push one from stack, which is going to be 3, and offset 1. So the 1 is going to be pushed again. Yeah, then let's make a pop below top. Why not? Yeah, that is 6. basically skipping 1. And then we return. Initially there was nothing, and then let's do that. Well, let's make that even simpler, I guess. Yeah, let's only test individual instructions here. We push padding, because we can provide an initial stack. That is clean. That is super clean. So okay, yeah, push padding. Oh, that is cool. That is super cool. Yeah, push padding. Let's see. Pushes bytes. Okay, yeah, we are also testing the return instruction. I get that. So initially, if there was nothing, we don't actually want to test that. We only want to check that the length of that is 1. Well, yeah. Okay, yeah, this is kind of messy. So we have a program, we have an input, which is just going to be an empty array. True. Yeah, we want output. We want the length to be 2. That's it. We have nothing else that we want to test. Yeah, then push 1. Yeah. So if you run push 1 on an empty thing, then the output should just be 1. Simple. Let's also have the other, and let's try that with another byte. Okay, now if you push 2, yeah, it should be 2. Nice. Push 8. It's going to be a bit more complicated. Like that. Oh damn. Memory leaked. Oh no. How can that be? I mean, I know how that can be. Because we need to clean the output here. Like Nice. That's pretty cool. I like that. Oh yeah, that is nice. That is nice. I tend towards actually removing these because I mean all of these just test a single instruction, so it's not like you're really missing that much. Nice. Okay, so pushing an 8-byte thing. Yeah, then push 1 from stack. Let's test that. Push 1 from stack. We have the offset. Right, so let's say the input is actually 1, 2, 3. And we want to extract the 2. We'll do something like this. Okay, let's skip 2 elements. Take 1. Yeah, that should result in 1, 2, 3, 4, 2. No, like that. Yeah, like that. Nice. Then push 8 from stack. So here we have a 2 on the stack. Boom. Now we also have a 3. No, hang on, that's not how stuff works. Yeah, this more like this. Let's say we have a 2 on the stack, and also a 3. And then you have the instruction for push 8 from stack from offset 8. Then the 2 should be put on the stack a second time. Kind of like that. Oh. Have bounds. Look at that. Let's double check that this is correct. Oh, it's not, because this is supposed to be a 64-bit one. Yeah. Okay, push 8 from stack works. Then pops an amount. 3 things from the stack. 1, 2, 3, 4, 5. Popping 3 things results in 1 and 2 being on the stack. Amazing. Then pop below top. That's an interesting one. That is really an interesting one. But it is pretty late. Okay, you know what? I'm gonna do that because then I have all these these stack manipulation instructions later. Top below top. That would be instruction numero 6. 2, 3, 4. Okay. So we skip, I don't know, 3 numbers, and then we pop 2 below. Yeah, skip 3 numbers, pop the 2 below. Nice. I think it's really nice having, you know, some, not just some testing in the code, but having this sort of nice tests you, because if this works, then I'm basically, I'm super confident that this works. And this is also nice documentation about how the instructions behave. And if you have your own implementations, you can just easily run these tests. That's pretty cool. Yeah. Alright, pop below top. Next we have jump. Jump is interesting because it's relative, like it's jumping within the bytecode. How would that look like? I guess let's just jump to that is 10. To this byte maybe, which would be at position 9, I believe. And you're having 1, 2, 3 as a stack that just returns 1, 2, 3. Because then we just jump to that return and execute that. Then jump table, that is interesting though. That is really interesting. Jump table. You know what, actually let's put a push in here. Let's say we have some sort of push 1. Yeah, exactly. Push 1 and return. And push 2 and return. And we are jumping to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hang on. That is the payload. Yeah. 9, 10, 11, 12. Let's jump to instruction number 12, which pushes a 2 to the stack. Like that. And jump table actually contains the number of different jumps that we have in here. So let's have 2 versions of that actually. So jump table has 2 jumps, it consumes the 0. And these 2 jumps, they basically tell us, well, hang on, yeah, via this thing. And the first jump will jump to position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Then we'll jump exactly here, and this is where we'll have a push 1 instruction, and we return and the second one will push 2. I don't know. So that would not be 18, but that would be 19, 20, 21. Yeah, and if there's a 0, then we push a 1. If there's a 1, then we push a 2. Let's see if that works. Hang on, sig test maybe. That works. Nice. So next up, call, and I think call only makes sense with return. So let's do that. Let's have some sort of call and return, where we basically have a call, and I mean we use return all the time. We used that already, so yeah, the return will just return like that. So it's just gonna have an empty stack in the beginning and at the end. Boom. Sure. And push indirect. That is interesting. That can only be tested together with call indirect. So let's do that. Let's say we have, oh yeah, and call indirect can only be tested with return. So this would be push indirect, call indirect, and return. First we have push indirect. Next we have a call indirect. And let's put 13 in there. So this references push indirect 13 would push some token that represents this instruction. And the call indirect will pop that token and jump there, and that will return. Of course, the token will just be that number. Oh, that doesn't work. Huh. Interesting. The M213. Well, okay, yeah. Oh, opcode is read byte. Interesting. That maybe not correct. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, there. Yeah, that is actually 10. Oops. Hang on, then how does this work? 1, 2, 3, 4, 5, 6, 7, 8, 9. Sure. Call 9. Next 18, length 11. Now this is like 1 plus 8 is 9, plus this is 10. 1 plus 8 is 9, 10, 11. I think this one fails. Okay, so let's see what we do. We push indirect. Which means we read an integer. In our case that will be the 10. We push that to the stack. Then we have this call indirect, meaning we pop that 10 from the stack. Oh, I see. Yeah, so we call that code that returns and that returns to here, and that should again return. Interesting. I think that should work. Okay, you know what, let's debug print data stack. Empty, 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 10. $86. During the call indirect instruction. Oh yeah, this doesn't read an int from the bytecode. No, no. This just data stack.pop_int. That's how we get the target. That makes sense. Very nice. Very, very nice. Okay, so we have that. Yeah, push indirect. And call indirect and return. Okay, then adding integers. Yeah, let's put return in there because that's the official name of the instruction. Actually, let's put all the, like even in here, let's put the instructions in there so that we can more easily kind of recognize what's happening there. I mean, return is also tested here, I guess. Oh, what's going on here? You see? This is interesting. Next, adding things. I think let's just say we have not a 10 but a 1, I guess, and a 2 in the stack, and then we have this add instruction which is 2, 0, and then we return. That should result in a stack that contains just the 3. Please work. Nice. Then subtracting numbers will be similar, except the instruction is 2, 1. And let's say we have 5 and we have 2, that results in 3. Okay, next multiplying numbers. Again, 5 and 2, star instruction, something that results in 10. 5 times 2 is 10. Then dividing. Let's say 8 divided by 2 is 4. And here we should also check this one, that it rounds towards 0. Yeah. Then we have mod. It's basically 5 mod 3, I don't know, it's 2. Mod is 24, compare 0. Okay, yeah, compare 0 is the evil instruction. Like, this is the instruction where I have many errors. So I'm actually gonna check all possible cases. If there's a 0 on the stack, I want to compare that to 0, then we'll get equals, aka a 0 byte. If that number is greater than 0, for example, it's a 42, then we will get a 1. Amazing. And if it is less than 0, for example, in 2's complement, it is something like that, I will get a 2. Oh, huh. Spec in compare 0, 8. Expected 2 for 1. Oh, yeah, that makes sense. This is a little endian, so this is the least significant one. This has to be, as long as this is the last bit of this rightmost byte is a 1, things are negative, yeah. Okay, so then ending integers. I think that would be 30, sure. Yeah, let's have all possible variants in here. I mean, there aren't that many, so. Something and then zeros, and in here we'll have 0, 1, 0, 1, 0, 1, 0, 1. The result of that should be 0, 1, 0, 1, 0, 0, 0, 0. Amazing. Then we have the OR, which should be 1, 1, 1, 1, 0, 1, 0, 1. What else do we have? And or XOR. That would be 1, 0, 1, 0, 1, 0, 1, 0. No, hang on. 1, 0, 1, 0, 0, 1, 0, 1. Yeah. No, not quite. In XOR and also in OR. Okay, so let's see. In OR we have this. Okay, so I believe this should work. Let's make sure, yeah, these are seven zeros. The output is this. Or 8. what's going on there? Like 0, 1, 0, 1, I see that. Oh yeah, and then again 0, 1, 0, 1. Yeah, that makes sense. So here, both are 0. Here the second one is 1. Both are 0. Second one is a 1. That should be correct. Return fail. Oh, memory leaked. Interesting. Interesting. Hang on, how's the OR implemented? Because that should just be, well, yeah, quite similar to the AND actually, except with an OR. Oh, I see. We're using the AND instruction. Yeah, okay. Fair enough. Fair enough. Amazing. So XOR works as well. Yeah, now we have malloc and free. Also store and load and crash. Well, so let's work with that. Let's have malloc and free first of all. So I think what I want to do is malloc, store an 8-bit. Oh yeah, store 1 byte there, load 1 byte, free the original thing, and return. Crazy. So yeah, let's say we have allocate 1 byte of memory, alignment 1, with 1 malloc, which is for 0, yeah. Pops the alignment, pops the size. Then we want to store something, a byte. So what we do is we do push from stack. Push 8 from stack 0, 4. 1, 2, 3, 4. 1, 2, 3, 4. That kind of duplicates the address. Sense. Then we store a byte there. We can push the byte using this one, the push instruction, and we're going to push 42. So this will actually be malloc, push 1, store 1. Store 1 is going to be 42 in hex. Store 1. Yeah, it only uses the data stack. Stores that in memory. Next we have load 1. And that kind of consumes the address and pushes the byte instead, so that would be 42. Does this work? No, it does not. Okay, memory leaked. Interesting. Alright, because we never free that memory, that makes sense. That actually makes sense. That is pretty cool. Yeah, 42. So this does a store. What we want to do instead is, yeah, we want to store the 1, but then we want to free, no, hang on. Yeah, we do want to load the memory, but before we do that, we also want to duplicate that again. That number, yeah, then loading the memory, giving us the actual address on the stack than the byte that was at that memory address. So I think we want to push padding actually. 7 bytes of padding. Yeah, push padding. That is 0, 0. I want to push 7 bytes of padding. And then we want to push from stack again. There's 0, 0, 0, 0, 0. Oh, no, not quite. We want to push the one at offset 8. Because that is the address. Then we want to free that memory by calling free. Hang on, free also accepts the size. I think that actually, yeah, I think that should actually be the other way around. First there should be the size, then the address. I'm willing to change that in the spec. Yeah. First pops a size, 8 bytes, then an address, also 8 bytes. Yeah, cool. Let's not do that. Set sim malloc. Oh, that, you see, that is nice. That is really cool. That is a cool formatter, honestly. Push from stack 8 or something like that. I push 8 from stack. Then move this. Then move this. Store. We'll load that. We push padding. Yeah, we push 8 from the stack, from offset 8. We push 8. That would be, I guess, yeah, 0, 2, perfect. And the value that is 8. In our case, that is the same thing that we wanted to allocate. And then we free that memory. Beautiful. That is pretty cool. Yeah. Then we want to return. And hang on, we want to pop the padding. That's gonna be a pop. Yeah. Let's see. Okay, so this doesn't work. For loops or objects with non-equal length. Interesting. Thank you for the helpful message. Like, what are the lengths That's kind of what's interesting me. Let's see, malloc would consume all of this, pushing an address, aka 8 bytes. Then we push another 8 bytes, so we have 16 bytes. Then we push the 1, 17 bytes. Then we store the byte. Yeah, 42 stores the byte. Pushing 9 bytes, the byte and then the address. So we have 8 bytes left. Push those 8 bytes again, having 16 bytes. Yeah, we load the thingy, leaving us with like 8 bytes and then 1 byte of the payload. Pushing the padding, giving us 8 bytes. Then pushing 8 bytes from offset 8, so we have 24 bytes now. The length 32 bytes, then freeing 2 of those 16 left. We pop 7. And now what I want is pop below top. And below the top 8 bytes. Please want to push 8 bytes. I have to say that the zig formatter is really, really nice for these kind of bytes. That is pretty cool. Integer overflow. Pop below top. Oh yeah, below the top byte. We want to pop the 8 bytes below. Hey, look at that. That was work. And this is really good to know that this works. Really good, honestly. Yeah, I do want to make some small changes to the bytecode format actually, which is kind of sad. There's one thing I would like, which is that you have 00 be a lock instruction that does nothing. That is not really immediately useful, but it makes sure that you can just fill zeros in the instruction stream and that doesn't change anything. So you can just use 0 as padding. Yeah. I'm also thinking in soil, my previous bytecode, I have the first character be some sort of, you know, for example, for crashing, there's an error, so there's an E for that, and the hexadecimal encoding. To have these sort of mnemonics, you know, you can more easily, like I could just write bytecode by hand, and I think something like that is useful. Yeah. So I think I'm actually gonna rename stuff. These additions, divide, those are arithmetic instructions. So there will be A. These are just bitwise instructions, so these will be B. Yeah, then they are memory instructions. I don't know what to do about them. What else do I have? in terms of letters, you know, I have A, I have B, C, D, E, and F. E is already used for errors, so we have C, D, and F. For what exactly? For, well, this could be kind of control flow, C or F. You like jump table, call, push indirect, call indirect, and return. And these are kind of, I don't know, heap stuff. Oh yeah, and also these kind of general like push and so on instructions. It's kind of stack instructions, you know. F. What letters do I have left? C, D, and F. What could C stand for? What could D stand for? What could F stand for? D could stand for data. The question is that data, you're moving data on the heap, like pushing, popping values? Who's that data on the stack? Malloc free and so on. I tend towards using that for data. Using malloc free, store, and load instructions. They will have the prefix D. And C and F are still left. I could just say C is for general like stack control instructions, you know, padding, pushing stuff. And then F is for actual like control flow, jump tables, calls, etc. Yeah, I think I like that. Let's organize these differently, like alphabetically, so that the 00 instruction is at the front. Then we have the A instructions. Still like a double, yeah. Okay, yeah, then we have B instructions, the bitwise ones. Then we have the C instructions, which controls the stack. This is like also really nice. You can implement them from top to bottom and kind of see they kind of build on each other, you know. Like control flow stuff is perhaps the most complicated one. And it's like really cool that, for example, D0 is just malloc. You kind of get I think over time you can kind of get a feel for which hex code means what. I think it's way easier to remember than just having arbitrary digits for that. Okay, that means I'm going to change this in here as well. And 00 is actually just a not instruction that does nothing. that's it. And this push padding, push stuff, there's actually, these are control instructions. This is flow, control flow. Well, let's ignore the C. Then we have arithmetics. We have bitwise stuff. We have data stuff. And we have errors. Amazing. Yeah, let's maybe kind of reorder these. And let's put the A and B instructions first. And again, it also makes sense, you know, just looking at the instructions, because these are quite fundamental. Then we have the C instructions, the D instructions, the E instruction, and then the F instructions. Pretty cool. Pretty cool. Yeah, in the main file, let's also adjust how these are tested, which is by now quite a lot. So that's gonna be nice. So test. Actually, we have another instruction, test nub. That just has nothing in there. We have an input of 0 and the output is, the expected output is 0. I'll actually put multiple in there. Simple. Amazing. Yeah, these are control instructions. This is a control flow instruction. Push flow and return. It is pretty, you know, the fact that I can just remember these prefixes, that means it's quite useful to have them. Then push one. Oh yeah, there's flow, there's control. I see. Did I say the zig format is great before? I take that back. What the hell? But sure. change the instruction. Yeah. Towards push, return, push, return. Same here, push. Oh no. I think the program is actually the same, just the initial stack was different. So I can actually just paste that in here, in there, and that's it. Then calling something, which is control flow. Then returning, which is also control flow. Pushing something, calling something, returning something. Oh, call in, push indirect. Well, that is interesting. That's kind of in between. Yeah, I'm gonna count it as a flow instruction, I think, even though it just pushes something to the stack, because it is really related to control flow. Yeah. Well. Now we get to the binary instructions. And we have these data instruction, control, data, control, data, control, data, control, flow. Okay, I mean the fact that I can just remember, that you can just remember these because these letters really mean something. That's really great. That is really great. I should also test the push, the store 8 and load 8 instructions. So I malloc something, I malloc 8 bytes this time. And then I push that 8 again, I push a 0, 2, do a push 8, hopefully. See, C4 is a push hang. C2, that's what I have here. Oh yeah, and then I store 8 and it's D3. Oh. You know what would be really great? That would be D8. For that. Damn, that would be cool. I may change that actually. Not today, I'm just gonna refactor that and then move on, but that would be super cool. Okay, so loading 8. Then I don't need padding, I don't need to pop that. Here just store 8. I'll skip the top 8 bytes. Return. No, not quite. Integer overflow. Okay, what's going on? Let's go through this. We malloc memory 8 bytes, alignment 8, by the way. Then we push an 8 from the stack. We push the address on the stack 2 times. We also push a 42. Okay. We store 8. We load 8. Hang on, that is probably something else. Load 8 is D5. Yeah, okay, I mean the 8 doesn't really mean anything if there's an 8, so I think I'm actually gonna leave it like that. Leave that as it is right now. Oh, okay, this is cool. This is really cool. Like that is a cool error. Here. Oh, allocation alignment doesn't match. Did it say free alignment? Does free need an alignment? In Zig. I mean, sure, let's do that. Let's do that here as well. You know, give free the same information as malloc. First pops alignment, then the size, 8 bytes, then an address. Something like that. Yeah, and here we'll actually push the alignment of 8, and here we'll push the alignment of 1 exactly. And then our VM can actually, in the free part, it can actually do the alignment. Sure. How to get the alignment for that? Because the alignment probably has to be comp time zone. Yeah, I'm just gonna put that in there, I guess. We'll use the same thing but with a U16. There has to be a more elegant way than that. There has to be. Damn, that is ugly code, to be honest. Invalid free. Why that? What's invalid free? That is not an error message. Invalid free. What? That doesn't make any sense. Okay, you know what, let's, because I have a lot of this kind of weird code in here, let's actually have a separate heap. Let's say we create a heap. Let's define down here. We have function unit takes the alley, which is a standard allocator, returns this, and what it does is return something where LE is LE, like that. Okay, and then we have alloc, malloc, I guess. We have a size, which is a U size, and then alignment, which is a U8, and that returns you, I don't know, a U size, I guess. And then we do stuff, whatever we do for malloc. Yeah, you see this is already cursed, like this is pretty cursed. I think factoring that out into here makes sense. Yeah, this accepts self, which will be a star, like this, so mutable reference to self, so we can then use self to LE. Amazing. Create an int from a pointer, we bitcast that to an I64. I think that is fair. That is very fair, actually. And then free looks not the same, pretty similar. We can give it a size and alignment and the pointer. And then do stuff. What can we do? Well, exactly this. This one right here. Yeah, and we have the heap. We should also have a D in it, and then hang on, D in it. Yeah, we don't need a D in it, I think, because all of the values are freed automatically. Yeah, so the heap should be used for this one. So we can just do heap dot free. Same here, we can just say amazing. That does look pretty cool. Yeah, heap is var, and of course the alloc and malloc can fail. Of course it can. Oh yeah, that means down here this can fail. Which I'm okay with. Should be able to raise an out of memory thing. Oh yeah, this can apparently also fail the freeing. The memory if the alignment is weird. Oh, look at that. That was invalid free. That doesn't tell us anything. So after le.free, I see that. Yeah. That then calls self.le.free. I see that, yeah. Calls self.vtable.free. This one does, yeah. Well, okay, yeah. And now for the general purpose allocator, which is in standard heap general purpose allocator 865. We have this free large. I'm fine with that, yeah. This is that. Okay, so apparently we are freeing an address that we weren't even given, maybe? Looks like it, to be honest. I mean, in here, instead of int casts, should we just use the address like that, maybe? It has to be a use size. That is kind of cursed. Let's turn it into a bitcast, because that, I think that is more reasonable. Simpler, okay, sure. I don't quite know where that is happening. What is that doing? You know. This should work. Size, we have the alignment that we switch on. Invalid free. Yeah, let me maybe let's look at this one. Yeah, so this is not free, no, this is push one. So we have the address, we have the size, we have the alignment. In here we have the address, we have the size, we have the alignment. Seems reasonable. But apparently apparently it is not. Let's just print let's say address equals this. So we allocated this, then we free the same thing, I believe. Yeah, let's put some new lines behind that. Just test that again. Okay, so yeah, this is the same address. Same here. Yeah. Should work. Free, where's free? Here. Pop a byte. Pop the size. We pop the address. Seems reasonable. Invalid free. I don't get it. I really don't. Yeah, I think we're gonna stop there for today. Yeah. Well, see you in the next something. Okay, what's going on here? We allocate some address and then we free that same address. Then we allocate another address and we free that address. That should work. Like, what the hell? I think because it's the second allocation, this is in the second test. Let me double check that. No, it's in store 8, load 8, free. So that is down here. Interesting. Okay, yeah. So what we do is we free something with alignment 1. Oh, yeah, alignment 8. Does this code make sense? We malloc 8 bytes using alignment 8. We push that address to the stack, so it's on the stack 2 times. We then push 42, we store 42. We push from stack again of that thing. We load that value. Push it again, but offset 8. We push the number 8 and a 1. Then free takes that alignment, it takes the size, and it takes the original address. And free is done. Okay, and then below the top 8 bytes we pop 8 bytes and return. Hang on, the output of that should not be that, but that should be an 8-byte number, like that. And that's not why this is failing, this test, but still. Okay, so here's the loop is in here, and there's the free. Let's maybe print some more stuff. Let's print freeing this. with the size and alignment. Okay, freeing something with size 8, alignment 8, that makes sense. Oh, hang on, in the allocation, I think, we do, okay, U8s. That's kind of weird, I guess. Yeah, size, alignment. Let's print that as well. Yeah, size 8, alignment 8. Well. Oh, I think the length is, yeah, the length is the number of items. And in this case, it's U16, that is actually the size of the memory divided by 2. This feels like such a workaround, like I'm working around the zig issues. Yeah. And I mean, this doesn't, like, we can have something with alignment 8, yeah, but size 9, we can't represent that in zig. Like, we can allocate that, sure, in here with an aligned alloc, but we can't represent that. I don't know why. What was happening when I just did free that thing? And that's it. Let me maybe check that out. Yeah, creating this once. Then it was complaining that the alignment was different, right? Yeah, the free alignment is 1. Okay. Okay, can we instead maybe only align that pointer? Align cast. Something like that. Like, I think you can just do, stuff like this. Aligned 8. Well, maybe not that. But you can do something like that. Let's see how that looks in here. Oh yeah, you can just do align. Align is a keyword. So if we do that, it's probably complaining that this pointer is not necessarily aligned the correct way. So this actually needs the alignment in there. Okay, that has to be comp time known. Fair enough. Yeah, which means that we'll have to well, hang on, how does alloc create a slice? Oh, okay. So this is a pointer that is aligned to the alignment of types t, and then they do 0 ... n. That seems so much cleaner instead of having this separate memory thing and assigning to that. So I can just do that basically to tell Zig, oh, by the way, it's aligned to that and that. Well, yeah, okay, the alignment stuff still. But that means I can basically do this. And then within the branches, I'll just do that. And no weird, size divided by 4, size divided by 8, These are all just pointers to bytes. So we can be very precise about how big they are. You can choose that on a byte granularity, but the alignment is separate from that. Oh, still, yeah, okay, I guess this is that. Okay, nice. I mean, this is really, this is complicated code, copied code. I think there should be a way to simplify that. I think I'll have some sort of alignments value. So that value const 1, 2, 4, and 8. These are possible alignments. Hang on, and this is a list of U8s. And then in here I can just do a comp time for maybe. And then do if a, so then we have comp time a, and then we can check if the alignment equals a. We can do that. Something like that. Is it called comp time for, or is it called inline for? I think inline. Yeah, that guarantees that the for loop is going to be unrolled. So in the code we'll actually just have a bunch of ifs, and then again, later on, these might be deduplicated. And here we can use a, which is a comp time expression. Okay, yeah, that is the buffer. So here we can say the buffer is that, and then we'll do this down here. Well, in there. And yeah, also returning actually. Yeah, and the else thing, let's do that down there. Okay. Is there a cleaner way to do that, to kind of not have this indentation here? I think not really. Yeah. I guess that's it. But yeah, we can do the same in here, and then we just have to have this one once. Boom. And that's it. Okay, so we have an address. Expected type something. In 304 in here. Address is not really, oh yeah, we're trying to return void. No. What's going on? Oh, and I copied this, yeah, I copied the align 1. That is supposed to be a line of 8. Okay, nice. Cool. I like that. Wondering, like, I don't like that this is really, this is so indented, so maybe I'll actually create a separate function for that then call. But there's a function with a comp time line. Look, internal, I don't know. And that just does this. And then in here, we'll just call malloc internal or self.malloc internal of the same size. And now we don't use alignment as an argument, but instead a, because a is a comp time value. Yeah, so we basically have this small wrapper around the actual alignment code that turns this runtime known variable which is one of a known set of values, turns that into a comp time variable. Yeah, then this is a bit more readable, passing the alignment and so on. Cool. And I'll do the same with free. Except with this content in here. And also the print should go in there because that's kind of like the actual paid with the actual stuff we want to do. We also get the address, which is going to be a usize that we then have available here, and this is just the alignment. Okay. Oh, A, which is the comp time version of the alignment. Cool. Cool. Yeah. Incompatible types. What's going on there? Oh, I think that first of all we should do an early return here. And same here. Because otherwise we always return invalid alignment. Expected type usize found I64. That is hang on, free internal with the address. Sure. Oops. Yeah, true. That returns void. Nice. Okay, let's remove the debug prints and just run that again. Okay, and we have tests. Pretty cool. So we've basically written a low-level bytecode machine that is working, where you can specify your program as bytes, and yeah, you can execute them. You can say, well, this is my program, call that with this input that you put on the stack, and the output is the stack afterwards. That is pretty nice. Yeah, I think yeah, that is nice. Just saying, run this program, please. Cool. I think that's it for this video. And yeah, next up would be actually compiling Plum opcode to this bytecode. So see you then. Hang on, I'm just realizing some kind of CLI would be nice. You know, being able to say ground, like in the terminal, you know, being able to say ground and then having some file.ground and that program gets executed. I think I want that. So let's write a little like wrapper around this thing. What is root? I think root is actually the, if you use this file as a library, I think root is included. So let's maybe rename VM to root and import that run function from root up there, and also move the tests over there, I think, because they really belong to the, well, to the VM. Okay, nice. And then this is quite small. Amazing. Yeah, let's try that out. Test root. Okay, all tests passed. Amazing. And now we can look at the main function and kind of, you know, zig build run, I think, is what builds and runs the code. Yeah. Hello ground. Opcode to yeah, right, we changed the opcodes. So pushing something is something like C2 actually. And adding things is arithmetic stuff. This is control flow. This should work. Yeah. Alright, so the question is, what do we want to do? I think you should be able to call the ground program. That should first of all create an allocator. That is fine. This is also fine. Then we want to open some sort of file. That you have to provide as an argument to the program. I'm not sure how that how handling arguments works in Zig. Let me double check that. Okay, I've opened the browser, nothing else. Let's see, we do something, the input, what is in, oh, it's like in here. Let me maybe look at some examples which are more code samples. Printing hello well, okay, calling external library functions, okay, memory detection, I guess, C interoperability, zigzag, the fizzbuzz thing, the generic types. Yeah, sure, using curl. Does this have no, it doesn't use arguments. Zig use process arguments. And I know the philosophy of Zig is more like, you know, just look at how the OS does that. But I'm pretty sure, yeah, the standard library contains stuff for that. Why does this only compile with var? Oh, because we makes sense though, because this right here changes the state of that variable, so it's not a constant. Okay, so we skip the min, then args.next. That is a try. No, hang on. Args.next is that cannot return an error. That's cool. Can return 0, which I think we can catch with else. In which case we're actually going to write to standard error. So let's have like a standard out file and standard out, and the same with standard error. And let's hopefully get standard error. Well, let's not use that. Let's not buffer that. Standard error, because that's going to be used in a lot of code. Hang on. Yeah, standard out. Oh, these are not used. That's true. So if there is no name, this will be the file name. File. Sure. Yeah, then what we'll do is we will print to standard error. Usage ground file. And then we do standard error. No, we don't need to flush that. Instead, we'll just exit. Is there something here? Yeah, there is. Exit with 1, maybe. Beautiful. Otherwise, we now have a file path. We have we have an allocator. Oh, args.next actually expects an allocator. Sure. Then we're going to read the file. Is that like a standard file system? Standard fs read? Nope. So read file. Read entire file. That will look promising. This seems nice. What was that? No, this really is that. Oh, come on, like, do I have to really like open a file, create a reader, stuff like that? Current working directory. Read file alloc. Oh yeah, expects an allocator, a file path, and then a maximum size in bytes, which will put to like a kilobyte file. I think that's fine. If the files are larger than max bytes, max bytes, returns error file too big. Okay, that's nice. Okay, so then this just returns a slice. That's really cool. That is basically the program. Then what we do, I think when you just call ground with some ground file, the program should run. So that's just gonna be program. Oh yeah, let's put a try in there as well. And the input, I believe, should just be nothing. There should be nothing on the stack. Then we do not a debug print, but instead just standard out dot run file. Running program, something bytes with the program.len. Yeah, and then printing the output. Ran program output. And then for every byte, so basically for every output byte, we'll just do standard out dot print the byte. Okay, now we go. Now we can do this. In hexadecimal, 0 right aligned 2. Yeah. And then in here we flush that. Then we free the output. Let's defer that, do that here. Like, I can defer li dot free output, and the program maybe as well. Yeah, defer freeing the program and the file path. Oh, defer. Quite important. Okay. Let's see what happens. Oh, something. I don't feel I remember a function named writer on generic writer. Okay. Well. Oh, can we just, is that already a writer? Can we just do that? That would be cool. Yeah. Nice. Okay, so args.next. Hang on, that doesn't need allocate. Okay, I guess that makes sense, yeah. Maybe. Yeah. Because that just points to the internal buffer. That's somewhere on the stack already, so yeah. Okay, hello ground, user just that. Amazing. What if we put something there? No stack named directly that to pass that to our program. Yeah, file not found. Okay, that is fine. That's nice. Yeah, let's maybe do some more error handling, I guess. Yeah, let's do error handling here, reading the file. Instead of just doing that, we'll actually catch the error and switch on that. File too big. Is it like that? Then we'll just print file too big, I guess. Like that. File not found. print file. Oh man. Okay, so there is a lot of stuff that can go wrong here, I guess. Antivirus interface. Why? Okay, sure. Yeah, no, we're gonna not handle everything. Otherwise, we'll just return the error. Oh, and in these cases, we'll exit with a 1. Indicating an error. Cannot format slice without a specifier. Okay, yeah, I guess where's the coming from? Oh, from here probably. Hey, you're having an error. Trace spec, that would be really nice. Oh, file FDS not found. Nice. That is really nice. Okay, so we now have. Now we can just do zig build. I don't know if there was anything. What does that do? Is that there's a debug build? Can we do build release or something? Oh no, never mind. How does that work? So we have standard stuff. Add executable. The name of the executable, I think, is just gonna be called ground. And the library is also gonna be ground. Build release, please. Yeah, optimize is release safe. And in our case, optimize is standard optimize options. That can probably be changed using a command flag or something. I see that this one right here, probably. The optimize is release fast. Oh yeah, that takes a bit longer, makes sense. But now in zig out, we probably have, in bin, we have this ground thing. And we can also remove the ground. Zig 1, perfect. Okay, that's pretty cool. Nice. So let me actually put this folder into my path. So I think that works by just putting that in my bash lc, which is a hidden file. I don't know if I should show this stuff on YouTube. I guess that is probably fine. Oh yeah, these are hidden files. This looks fine. Bash lc. Yes, there's some path stuff in here. Okay, so let's also add to the path this one. Nice. And now, if I open a new bash session, I can just do ground to run ground. Okay, that's pretty cool. All right, yeah, I got that working. Yeah, now I'm done. So like this is the end of this video. Now I have a VM that I can use, that I can just throw ground files at, and they get executed. I think I should actually like have one example ground file. Maybe one that adds two numbers. I don't know. Example.ground, and let's say this. Edited this with a hex editor. Yeah. So writing hex code out. I see. So first we'll push a value. Which was like push 8. C something. Push 8 is C2. Okay. So we'll do C2 of an 8-byte value, and first maybe a 2, which is a little endian encoded, so 1, 2, 3, 1, 2, 3, 4. Okay, then another C2 of A3 maybe. And then an addition which would be A0. Saving that. So 3 instructions. First, pushing A2 to the stack, then pushing a 3 to the stack, then adding those two numbers together. Now we should be able to just say ground example of ground. Invalid opcode 20. Interesting. 20. That doesn't make any sense, does it? Is it really this program? I'm wondering. If I do this and build that again, not fast one this time, but still, yeah, we do get stuff there. Oh yeah, we also need to return, by the way. The program needs to end. Why doesn't it store whether it uses hex editor? That would be weird. Okay, that works. Nice. Let's actually, let's comment this out again and build that again. We don't need the most optimized one. Fine with that. Okay, that works. When program output, and then you have the output. Actually, let's make that slightly more beautiful by putting spaces in between the bytes, and also printing a new line at the end. Yeah, just a new line. Okay. Nice. This is cool. I think this is what I'm gonna end with. Yeah. Next up, emitting ground files, compiling two ground files. But pretty nice. Yeah. See you in the next video.